All right, so these these are the sum and difference formulas that I want you to add to your notepad, to write on your notepad. And we're going to be using these formulas a lot. We're going to be using uh, these ones and these ones the most. Well, actually, all of them. We'll be using all of them in this lesson. I'll show you examples on how we can use some of them. I want to start with these addition ones, the sign of alpha plus beta. What it's saying is that the sign of alpha plus beta, right? And alpha and beta simply represent two angles. It can be any two angles. It can be sine of x plus y. It can be p plus q. It can be any two angles. Micah plus Mikhail, Short plus someone. It can be any two angles as long as it's any two angles. Yeah. So what it's saying is that if I have the sum of two angles, that's why it's called the sum identity, If I have a sum of two angles, then the sine of that sum is going to be equal to sine of the first angle times cosine of the second angle plus cosine of the first angle times the sine of the second angle. So what it's saying, I'm going to use x and y because I just like x and y. If it's sine x and y, then the expansion for that will be the sine of the first angle times the cosine of the second angle altogether plus, and I want you to notice how this plus sign over here is conserved here, right? I want you to notice that because in the difference formulas, something interesting happens as well. So sine of the first angle times cosine of the second angle plus cosine of now the first angle times sine of the second angle. You might be wondering, how is this even possible? How come? etc. I'm going to prove it for you. And since this is a video, it's not class, I have the time to prove it for you. If you're not interested in watching the proof, you can just skip ahead X minutes that the proof is going to take. But hope you see, yeah, never mind. Okay, so imagine that I have two triangles. Imagine I have a triangle like this. Not imagine, I actually have two triangles. That's supposed to be a right angle triangle. Let's try to draw better. Mr. William. No. Still not a right angle triangle. Okay, right angle triangle. And I have another triangle on top of that one, right? So I have another blue triangle. Let me draw a blue neat triangle on top of this one. Yes, okay. Now these two triangles are starting at the same position. So just stretch this one out a little bit. Starting at the same point. And this one has an angle, let's call this angle x, and this angle y. Yeah, angle y. Let's write x in blue. X and y in red. Alright, so I have those two angles. Then I also have this line here, the vertical line that's supposed to be shape recognition. I have a vertical line that's dropping down from the top, or let me write in yellow, from the top of this blue triangle to the bottom of this red triangle. Is that bright yellow line? Okay, so let's say this blue triangle has a hypotenuse of 1 unit, right? That's the only condition that we're using. It has a hypotenuse of 1 unit. Let's start labeling the sides. If this is A and that's B, this is the right angle triangle, that's the right angle triangle. We can call this C, that point is B. We can call this point E. I'm going to create another point here, which will give me another triangle. I'm going to create another point here, calling it this point here. That makes a triangle with that section. I hope you see that little right angle triangle. Let me call that point F. Point F. So I'm trying to figure out what the sine of x plus y from this triangle is. What the sine of x plus y? Well, if I use the triangle ADE, that big triangle with the yellow line as the opposite of x plus y. If I use the triangle ADE, I hope you can see that the sine of x plus y is equal to the opposite, which is DE, divided by the hypotenuse, which for the blue triangle, its hypotenuse is this hypotenuse over here is 1. So I see that sine of x plus y is just equal to DE, right? But something else that I see is that DE can be cut into two parts. D to E is the same thing as D to F plus F to E. D to F plus F to E, right? So instead of saying sine DE, it's just going to be sine DF plus FE. DF plus FE, awesome. Now DF, I can figure out what DF is, but I hope you can see that FE is the same thing as CB. FE is the same thing as CB, right? FE and CB are the same thing. So at the end of the day, my sine x plus y is equal to DE, which is the same thing as DF, which I don't know what that is, but I'll figure out, plus DF plus FE, and FE is the same thing as CB. Now, I need to figure out what DF is. I'm going to use this triangle which has the yellow opposite and the blue hypotenuse, that little triangle that I'm drawing over. So, since this angle down here is y, I hope you can see that if that angle is y, this angle inside here is also y. And if the angle inside there is y, that angle up there is 90 minus y. 90 minus y. So 90 minus y. I'm figuring out what df is. I hope you can see that the sine, if I'm at this point, using that little red triangle that I've drawn over, I'll write it down this way. The sine of 90 minus y is equal to df divided by dc. Sine 90 minus y is the same thing as cos y. We talked about this a bit ago, and we're going to talk about it again because it's a cofunction. It's what you see here. Sine 90 minus some angle is the same thing as the cosine of that angle. So the cosine of y is equal to df divided by dc. Now I need to figure out what dc is, and I'm going to take you over here for a quick second. DC is the opposite of the blue triangle whose angle is x, right? So from that triangle whose angle is x, the sine of angle x is the same thing as DC divided by the hypotenuse, which is 1. So sine of x is equal to DC. DC is basically sine x. So instead of having DC here, over here, I'm just going to replace it with sine x. So the cosine of y is equal to df divided by sine of x. And df, if I cross multiply, I'll end up with df is equal to sine of x times cosine of y. So back to my equation that I'm trying to prove for sine of x plus y, I already know what df is. df is sine of x times the cosine of y. See, I'm halfway there because I have half of it already. I need to figure out the other half, which is CB. CB, because remember CB was the same thing as FE. So CB is the opposite of the triangle ABC. I'm going to work in this small square up here in green. In the triangle ABC, the sine of y is equal to CB divided by AC. I hope you can see that AC is the adjacent of angle x in the blue triangle. So if I use the cosine of x in the blue triangle, the cosine of x will be equal to the adjacent, which is AC, divided by the hypotenuse, which is 1. So the cosine of x is simply equal to AC. So in this formula here, instead of having AC, I'll just substitute it with the cosine of x, and I'll end up with sine y is equal to CB divided by, instead of AC, I'll just have cosine of x. So I can see there from there that CB is equal to cosine of x times the sine of y, which is this over here. So I'm going to replace, instead of CB, I'll just sub in what I got. So initially I had sine x cosine y plus CB, which is cosine x times the sine of y. This is sine of x plus y. So that's the proof for this double angle identity. Sorry, not double angle. It's a proof for this sum identity for sines. We'll talk about double angles in a bit. So that's the proof for the sine identity, the sum for the sine. If you do the one for the cosine of x plus y, if you kind of follow these ideas that I've used here, you'll find that the cosine of x plus y is the same thing as cosine x times cosine y minus sine of x times sine of y. If you follow the same principles of the angles that I've used. And since I have the ones for the sums, I can figure out the ones for the differences. I have that sine of x plus y is equal to sine x cosine y minus cosine of x sine y. If I want the difference, sine of x minus y, I just because I know that negative y, sorry, subtracting y is the same thing as adding a negative angle, right? So in the positive identity, instead of having a positive y, I'll be adding a positive negative angle. I'll be adding a negative angle. So instead of having y in each of these cases, I'll just replace y with a negative y. When I replace y with a negative y here, sine of x cosine of negative y minus cosine of x times sine of negative y. When I replace, I know cosine is an even function, so that doesn't matter. So I will just say sine x cosine y. Sorry, this was supposed to be plus. Apologies. Plus cosine x. Instead of sine negative y, I know that this is a negative function, so the negative will come outside, and that's why for the difference, that's why I have a negative cosine x sine y. Now all of this is just showing you the origins of why these why these compound angle identities or sum and different identities look the way they look. You don't have to know how to show all of this. I'm just showing you for those that are interested. Moving on, if I want to use those identities to figure out the value of cosine 75, now again you'll be asking yourself, why are we doing it this way? Why am I not just putting this in a calculator? I'm telling you again, guys that did this math first did not have calculators, and the reason you're doing it, even when you have calculators, is A, it helps the thinking process, and B, it helps you apply this work easier because you know what the origins or roots of it are. So I need to break down this angle into two angles whose ratios I know. For example, I know 75 is the same as 90 minus 25, right? So if I wanted, cosine of 75 is the same as the cosine of 90 minus 25. I know the ratios for 90, but I do not know the ratio. Wait, this is not right. Not 25. It is 15, right? 90 minus 15, yes. I know the ratios for 90, but I don't know the ratios for 15. So this kind of notation or representation would not help me. I need to use angles whose ratios I know. But if I tried cosine, instead of 75, I can try 45 plus 30. Now, since I have 45 plus 30, I can use the addition formula for cosine, which will be cosine of 45 times cosine of 30 minus sine of 45 times sine of 30. The cosine of 45 I know is root 2 divided by 2. The cosine of 30 I know is root 3 divided by 2. The sine of 45 is root 2 out of 2. And the sine of 30 is 1 out of 2. Simplifying this gives me square root of 6 out of 2 minus square root of 2 out of 2, which you can write as square root 6, not 2, square root 6 minus square root 2 all divided by 2. Another example, find the value of sine 7 pi out of 12. Now, some of you are excellent at thinking in radians. I personally am not. So I'm going to first figure out what this angle is in degrees. And then when I figure out what angle it is, I can be able to think properly about it. So this angle in degrees is 7 times 180 divided by 12, which gives me 105 degrees. Okay, so now I know it's 105 degrees. I know it's in this quadrant over here, the second quadrant. And I know that a sine in that quadrant is still positive. So I'll just be looking for the acute angle in this quadrant that has the same sign as 105. Well, 180 minus 105 is 75 degrees. So that acute angle is 75 degrees. That means that the sine of 105 is the same sine of 75 degrees, right? And I hope you can see how helpful this is if you are someone working 900 years ago, 900 AD, and you don't know, see how helpful it is for you to know that these angles are have the same ratios because they're in those quadrants, and then being able to work with smaller ratios that you know. And 75 we've just seen is the same as 45 plus 30. And then going back down, I know 45 is the same as, because I want to work in radians, 45 is the same as pi over 4, and 30 is the same as pi over 6. So I'm going to rewrite this and say the sine of 7 pi over 12 is equal to the sine of pi over 4 plus pi over 6, right? Then I'm going to use the addition formula for sine, which is down here, the addition formula for sine, which says that this will become sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. Now I know sine pi over 4 is root 2 divided by 2. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. And sine of pi over 6 is 1 out of 2. So I end up with square root of 6 divided by 2 plus square root of 2 divided by 2, which gives me square root of 6 plus square root of 2 divided by 2. Similar to the last one, because the angle is the same and because the function is sine instead of cosine. What if I want to write this in terms of sine and cosine? Well, I hope you see that we have two angles. We have this angle, right?